Hello everybody, welcome back to another video. For this one, we're going to focus on polynomial divisions. Polynomial is really nice in algebra, in mathematics in general, and polynomial is really the function version of natural numbers. It has a lot of properties that are similar to natural numbers, and it behaves a lot like natural numbers. Um, for example, the relationship between a natural number, here 7,935 is really this number is just 7,000, so 7 times 1,000 plus 9 times 100, right? 900 plus 3 times 10 plus 5, and 1,110, these are all powers of 10. So I can also write this as 7 times 10 to the third plus 9 times 10 to the second plus 3 times 10 to the first plus 5. If I write numbers like this, it then resembles heavily as a polynomial, right? 7x to the third plus 9x squared plus 3x plus 5. In other words, if I think about this polynomial, plugging in x equals to 10, I will get back to the number 7,935. So polynomials are essentially the natural numbers of functions. Just to remind ourselves what's happening, we're going to go ahead and do a long division of numbers. So 3,814 divided by 12, we set up our long division, 3,814, right? We put that under the division sign here, divided by the divisor, which is 12. And now I need the first two digits, right? Because my divisor has two digits. So I asked myself, how many 12s goes into 38? And the answer here is 3. And then 3 times the 12 equals 36. I subtract 38 minus 36 is equal to 2. I then drag down the 1, right, because I need two digits here. And I ask myself, how many 12s goes into 21? And the answer here is 1. 1 times 12 is 12, and I subtract one more time. 21 minus 12 is 9. I one last time drag down the 4. And the same question, right? 7 12s goes into 94. So 7 times 12 is 84. Subtract 94 minus 84 is equal to 10. And at this point, 10 is too small to divide 12. So I know that is the end of my division. So the answer for this long division is just 317. At first, we write that as remainder 10. But then as soon as we learn about fractions, right, we then say this is 317 10 over 12, right? We write that as a mixed fraction, but we know that's really just a lazy way of writing 317 plus 10 over 12. The over 12 part, right, that 12 right there is the divisor. Okay, so this is the way of how we're going to write remainders with long division. So now, we remind ourselves what long division looks like with numbers. Let's take a look at long division with polynomial. And there is going to be a lot of resemblance. So we set up the polynomial, the long division in the same way. We write our long division sign here. Okay, on the inside, we put our dividend here. So 2x to the fourth plus 5x to the third minus 18x squared plus 19x minus 15. And that just a little bit. And then now I put my divisor, 2x minus 3. Just gonna go ahead and fix that a little bit. Okay, so now for long division with polynomials, it sometimes is actually a little bit easier because I only have to focus on the first number, the first term of each polynomial. So I just focus on the first term. I kind of ask myself the same question. How many 2x's goes into 2x to the fourth? But in terms of functions, there's a slightly better way of asking that, right? What do I need to multiply 2x by to get to 2x to the fourth? That's essentially how we ask ourselves back here, right? What do I need to multiply 12 by to get as close to 36 as possible? It's the same idea. So here, I know I need to multiply by x cubed. Once I make that decision, I then take this x cubed and then multiply to both on all terms of my divisor. So x cubed times 2x is 2x to the fourth. X cubed times negative 3, it is negative 3x cubed. And then just as before, I'm going to subtract. By the way, the reason why I like to put a little circle here is because if I don't put that little circle here, it looks like that subtraction is only affecting the 2x to the fourth. But in reality, it affects both the 2x to the fourth and the negative 3x cubed. Okay, so just kind of out of a good habit, I like to put that little subtraction sign there with the circle, just so I don't confuse myself, especially if I'm trying to rush through this problem. Okay. Anyways, so 2x to the fourth minus 2x to the fourth, that goes away. That's the whole point of this. And I have 5x cubed minus negative 3x cubed. So minus negative, double negative, gives me a positive. So I have 5x cubed plus 3x cubed. So I have 8x cubed. Now I drag down the negative 18, negative 18x squared. And then I rinse and repeat. That's my first step, right? So my second step, same idea, focus on the first term only. Ask myself, what do I need to multiply 2x by to get to ax cubed? And the answer here is 4x squared. And then I distribute to both of these, both terms of my divisor. 4x squared times 2x is ax cubed. 4x squared times negative 3 is negative 12x squared. I'm going to subtract. Ax cubed, they cancel each other out. A negative 18x squared minus negative 12x squared is negative 18x squared plus 12x squared. It is negative 6x squared. Drag down the positive 19x. Next step, we focus on the first term here, the negative 6x squared. Ask myself, what do I need to multiply 2x by to get negative 6x squared? And the answer here is negative 3x. Okay. Distribute to both. I have negative 6x squared plus 9x. And I subtract. The negative 6x squared, they go away. 19x minus 9x, it is 10x. And I drag the last number down. Okay. My very last step, I ask myself, what do I need to multiply 2x by to get to 10x? And the answer here is 5. So I distribute to both terms. 5 times 2x is 10x. 5 times -3 is -15. And I subtract. Both of these is going to cancel each other out. 10x minus 10x goes away. -15 minus -15 goes away. So I just have 0. And that is it for my long division. I know to stop because the number I have is no longer going to have a high enough degree to divide my polynomial. My divisor is a degree 1 polynomial, and the remainder here, I know that is the remainder because that is a number, which is sometimes known as the 0 degree polynomial. Okay, so when the degree is less than equal to the degree of the divisor, then you know you can no longer divide, and that is the remainder. So in this case, we have a remainder of 0, and then the answer is actually just going to be this thing right up here for my division. Okay, so that is basically it for this long division. It's long, but it's really not that difficult to perform, and it's really something that's really kind of useful and very similar to the stuff that we did even in the long division of numbers. Everything is very similar. In fact, I think this one is a little bit easier because you never have to worry about uh, anything else other than matching up the first term. Okay, let's take a look at the next example. Here we have another long division, but this one is a little bit different in the sense that the dividend here is okay, it's just as usual, but the divisor is missing a power of x. So it's not exactly a descending order of power. So what we want to do here is to put a placeholder. So the setup of this question, underneath the division sign, we got 5x to the fourth minus x cubed plus 6x squared minus 4x minus 7. This is all nice and good. But instead of writing directly x squared plus 2 for the divisor, I'm going to write x squared plus 0x plus 2. That way, I have a descending order of power. This way, when I perform my long division, I don't have to worry about remembering to put the division in the right place. So here we go. We focus on the first term. Okay. I see that I need a 5x squared. So then when I multiply by x squared, I get the 5x to the fourth. And then I distribute to all three terms here. 5x squared times x squared is 5x to the fourth. 5x squared times 0x is 0x to the third. 5x squared times 2 is 10x squared. And then I'm going to subtract. The 5x to the fourth go away. Negative x cubed minus 0x cubed is just negative x cubed. 6x squared minus 10x squared is negative 4x squared. And then I drag down the next line. Okay, the next term. So then I rinse and repeat, right? That's my first step. Rinse and repeat here. What do I need to multiply x squared to get to negative x cubed? Well, I will need a negative x. I want to distribute that to all three terms here. Negative x times times x squared is negative x cubed. Negative x times 0x is 0x squared. Negative x times 2, of course, is negative 2x. Subtract. The negative x cubed, they go away. Negative 4x squared minus 0x squared. Nothing happens, so negative 4x squared. Negative 4x minus negative 2, right? Again, the double negative becomes a positive, so I have negative 2x. And I drag down the minus 7. So now I need to multiply both sides by, multiply the first term by negative 4. So I can match x squared with negative 4x squared. So distribute that negative 4. We get negative 4x squared plus 0x minus 8. And subtract. So the negative 4x squared, they cancel each other out. Negative 2x minus 0x is still negative 2x. Negative 7 minus negative 8 becomes negative 7 plus 8, which is positive 1. And at this point, I notice that the degree of my polynomial on the bottom, it is 1, right? The degree of this polynomial is 1, whereas the degree of my divisor is 2. So just like before, when the degree of my polynomial that's left inside the long division is less than the degree of my divisor, I know that's the end of my division, right? I can no longer perform any sort of division. So that right there is the remainder. So the way you want to write down your answer is just like before. I'm going to write equals to 5x squared minus x minus 4, but plus the remainder is going to be negative 2x plus 1 all over. I'm going to write the divisor, but this time I do not need the placeholder anymore because I'm not doing the long division anymore. So x squared plus 2. Right, again, that right here is simply just the divisor of the original problem. Okay, so that right there is how you want to write the remainder part for a long division, or really for any sort of polynomial division. Now, this is really it for long division. Really not too difficult of a task. But if you take a look, if you think about this real quick, the powers of x's that we wrote in long division doesn't really do much in terms of calculation other than align specific numbers together. See, going back to example A here, the x to the fourth column, right? We have an x cubed column, x squared column, and we have a x column. Okay, the main point of these columns are essentially just align these coefficients together so they interact together with the coefficient of the same power, right? It's the same power of x's. So there's really a lot of redundancy here. If we can guarantee to work with the same type of numbers, we can actually drop these powers of x's, right? Because essentially they're the thing that's really making this process kind of longer than it needs to. So the next type of division is going to basically handle this problem. Here's synthetic division. Synthetic division is shorter and is faster, but the problem here is that it is weaker. So for polynomial, long division is universal. You can almost divide any polynomial as long as the dividend has a higher degree than the divisor. But for synthetic division, you can only use this when the divisor is a linear polynomial. In other words, it's a polynomial of the form ax plus b. Okay, ax plus b. So let's take a look at some examples here. The setup of synthetic division is pretty simple, right? Again, it's supposed to be a much shorter way of doing this. Instead of writing out the whole dividend, I'm only going to write out the numbers, the coefficients. So 3, 5, -4, -5, and -2. And instead of writing this thing here, the division sign here, I'm just going to not worry about that line right there. And in fact, this thing on the side here, I'm just going to go ahead and write a nice box instead of a little weird squiggle. What I'm going to put in this box is not the coefficients of the divisor. Instead, is the number that's going to make the divisor equal to 0. In other words, I'm going to put a number such that x plus 2 is equal to 0. And of course, this is pretty obvious. I just subtract 2 on both sides. We get x equals to -2. And that's what I want to put in that box. That is my setup for this synthetic division. Okay, I'm going to draw this line on the bottom. And to start this division, I'm going to drag down this 3. Okay, so every time the numbers below the line, I'm going to multiply that by the divisor number. So in this case, just 3 times the -2. And then I'm going to put that result above the line for the column to the right. In other words, I'm going to put that here. So -2 times 3, it is -6. This time, the interaction between two rows number is plus. So 5 plus -6 is -1. So that is my first step. I'm going to rinse and repeat that. So -2 times -1, I'm going to place that number here. -2 times -1 is 2. Okay. Once I have that number here, I'm going to do -4 plus 2, give me -2. And then I rinse and repeat. -2 times -2, that here, right? -2 times -2 is 4. And then -5 plus 4, -1. -1 times -2 is +2. But then +2 plus -2 is equal to 0. And that last number is going to be the remainder of this synthetic division. The way you want to read off the answer, though, is if you kind of go back and recall the long division problem, the column with all the powers of x's are basically a line following the original dividend. But the answer part is going to be 1 degree less. So this column is degree 4, the answer part is degree 3. This column is degree 3, the answer part is degree 2. This part is degree 2, answer part is degree 1. So the answer part is going to actually lose a degree. So going back to this problem, the setup here is basically turning the dividend polynomial into a list of numbers, right, where we just write down the coefficients. So I can think to myself what these coefficients are, well, coefficients of. The 3 is the coefficient of x to the 4th, 5 is the coefficient of x cubed, negative 4 is the coefficient of x squared, negative 5 is the coefficient of x, and negative 2 is the coefficient of, well, nothing. So I'll go ahead and put that as 1, just to remind myself that's a constant term. Okay. But on the bottom, all of the polynomials, right, all of the term loses 1 power. So 3 is now the coefficient of x to the third, negative 1 is the coefficient of x squared, the negative 2 is the coefficient of x, and the negative 1 is the coefficient of nothing, aka the constant term. You don't typically write these powers of x's up here. This is entirely for the presentation purposes, I guess. But that is the way that you should be thinking about. And the final answer for this division is just going to be 3x to the third minus 1x squared minus 2x minus 1. I know you don't typically write a negative 1, the negative 1x squared there, right? The negative 1. But again, that's just, for me to show you what's happening here. You don't have to write a negative 1. Okay? So in this case, the remainder is 0. That means the division just resulted in this particular polynomial. As we can see, it's very, very easy in terms of the actual division. It's very short to write down. It's just more efficient overall. The only drawback, of course, is that it only works with a linear divisor. Okay. Take a look at one more example here for part B. I'm going to go ahead and set this up. So writing down the coefficients. So 1, negative 6, 13, negative 13, 8, and negative 7. And then the thing that makes the divisor equal to 0 is equal to 2. Okay. So we are ready to do that division. Drag the 1 down. 2 times 1 is 2. We're going to add them. Negative 6 plus 2 is negative 4. 2 times negative 4 is negative 8. 13 plus negative 8 is 5. 2 times 5 is 10. Negative 13 plus 10 is negative 3. 2 times negative 3 is negative 6. 8 plus negative 6 is 2. 2 times 2 is 4. And negative 7 plus 4 is negative 3. And that is the remainder for this division. You should definitely always check your division. The best of us will make algebra mistake or human error. It's just the way it is. So double check is quick enough for us to go through, right? And it's worth it so you don't make silly mistakes. Okay, I think this is done correctly. So that's it for this division. Now, again, to write down our answer, right, we remind ourselves that this is the 1 is the coefficient for x to the fifth, x to the fourth, x to the third, x squared, x, and constant term, respectively. And then on the bottom, they lose a power. So this is x to the fourth, x to the third, x squared, x, and constant term. So my answer here is just going to be 1x to the fourth minus 4x to the third plus 5x squared minus 3x plus 2. And then I write my remainder, so plus negative 3 over the divisor. This time you want to put the divisor, right? Again, this is the divisor, not the 2 here, right? The answer is that. Okay, so the divisor is the x minus 2. Okay, so this right here is the final answer. So synthetic division can also handle uh, division that has remainders. Okay, and because synthetic division only works with linear divisor, the remainder will always be a number remainder, right? Because there's no other polynomials having lower degree than a linear polynomial other than just numbers, aka 0-degree polynomial. Okay? Okay, so this is an interesting situation. We're going to try to perform the synthetic division on this one. In fact, this is a familiar problem, right? We just did this not long ago. This is part B of the example of the long division. Now, let's play this out and see what happens. So the setup is the same. So writing down the coefficient 2, 5, negative 18, 19, and negative 15. But then what makes the divisor equal to 0 is 3 over 2. Right? If we think about setting that equal to 0, plus 3 divided by 2 on both sides, we get 3 over 2. So we put 3 over 2 here, and now let's go through the division. Drag the 2 down. 2 times 3 over 2 is just 3. We're going to plus 5 plus 3 is 8. 8 divided by 2 is 4, times 3 is 12. Negative 18 plus 12 is negative 6. 6 divided by 2 is 3, times negative 6 divided by 2 is negative 3, times positive 3, it is negative 9. 19 plus negative 9 is 10. 10 divided by 2 is 5. 5 times 3 is 15. And negative 15 plus positive 15 is equal to 0. So that is my remainder. It looks all nice and dandy until we take a look at what the answer is supposed to be, right? Again, just writing down the green, the power of x here is x to the fourth, x to the third, x squared, x, and constant term. That means on the bottom, I'll have 2x to the third, right? And then x squared, x, and constant terms like that. So my answer looks to be 2x to the third plus 8x squared minus 6x plus 10. And again, there's no remainder here, so that should be the answer. Except it isn't. Because we've done this problem, and this is the answer. This is the answer. So what is going on here? If we go back and basically write that answer down here, I'm gonna copy it over here. If we compare the two, we kind of see that they're very close to each other. In fact, the answer that we got from this synthetic division is actually simply twice as big as the actual answer. In other words, if we take the answer that we got from this synthetic division and we simply divide that answer by 2, we will go back to the answer that we're supposed to get. So what is going on here? Well, it turns out that the way we set up our synthetic division, we did not actually did this division. Instead, instead, what we did is we divide the dividend by this polynomial, x minus 3 over 2. But we can see that that is not the polynomial from part of the question. In fact, it is exactly half as big. In other words, the divisor, the original divisor, is 2 times as big as the actual divisor that we'll work with. Okay, that extra factor of 2 have to go somewhere, right? It needs to go somewhere. So you need to divide out that 2. And that's why it has to happen. That's why it has to have an extra factor of 2 on the bottom. Okay, so if you ever have to divide using this kind of linear polynomial, what you could happen is you set that equal to 0, and you find things to plug into this box. But after getting that result, getting a final result like here, we gotta take these numbers and we have to divide it by the leading coefficient of this divisor. So whatever answer we got, we have to divide it by the leading coefficient to get the actual answer of this division. Okay, so this thing is something that you do have to remember to keep track of, something that you have to do as extras, which is why a lot of time I suggest if you see this kind of divisor, if you see a non-monic polynomial, linear polynomial as a divisor, then it might be safer to use long division instead of trying to use this adjustment for synthetic division. But again, I still want to show you this because it still does work with synthetic division. Okay? You just have to interpret it correctly. Okay. Last example, synthetic division with polynomials that are not in the correct descending order of power. So here we got x to the 5th. You probably already guessed what's happening here. I'm going to leverage the placeholders. So instead of x to the 5th plus 1, I'm going to see that as x to the 5th plus 0x to the 4th plus 0x to the 3rd plus 0x squared plus 0x plus 1. So then the setup becomes 1, 0, 0, 0, 0, 1. And then in the box, what makes x plus 1 equal to 0? That one's easy to see, so just -1. Now I'm ready for the synthetic division. Drag down the 1. -1 times 1, -1. I'm going to add 0 plus -1 is -1. -1 times -1 is 1. 0 plus 1 is 1. -1 times 1 is -1. 0 plus -1 is -1. -1 times -1 is +1. 0 plus 1 is 1. -1 times 1 is -1. And 1 plus -1 is 0. Okay, so this one also has no remainder. And then we remember our polynomial start with x to the 5th, and then x to the 4th, x to the 3rd, x squared, x, and constant term. Therefore, on the bottom of each column, we lose a power. So we get x to the 4th, x to the 3rd, x squared, x, and then constant term. So our final answer for this division is simply 1x to the 4th minus 1x to the third plus 1x squared minus 1x plus 1. And you definitely do not have to write down all these ones. So normally you would just write x to the fourth minus x cubed plus x squared minus x plus 1. And that is the final answer for this synthetic division. Okay, so very easy to do here if you just remember these two processes, right? Long division and synthetic division. For long division, placeholders are technically optional. If you're very careful, you can do this without placeholders. But for synthetic division, placeholders are absolutely a must. So make sure you are not lazy about it and you do put the correct amount of placeholders. Placeholders can be for the dividend or for divisor, right? If you're working with long division. Okay, we've seen examples of both here. So both of these are very useful divisions of polynomials that does come up in various places in mathematics. Okay, so that's it for this video. See you guys in the next video.